Guys, I'm going to try to be quick. I don't know if I just started recording or not, but I'm going to try to be quick with this. I want to do a couple Hardy Weinberg problems with you, I hope. We might only just do this one, I'm not sure. So this should only be about a 10-15 minute video. But what I want you guys to do is get this down, okay? So if you haven't, hopefully you can see everything on here, okay? So, actually, I guess you don't need that top portion. So it says, in a small village, 15% of the population is born with sickle cell anemia. Sickle cell anemia is a disease that causes your red blood cells to be sickle-shaped, makes them harder to flow. We've talked about sickle cell anemia when we talked about genetic disorders. So this falls right along with that. And it asks several questions in particular, about this particular statement. 15% of this population in the village is born with sickle cell anemia, lowercase a. That tells you something there that it doesn't explicitly say. If it's lowercase a to have sickle cell anemia, that means that is for those of you who don't remember, that is the genotype, okay, right there. That means that the phenotype is, of course, sickle cell anemia. That means that it is a homozygous recessive trait. Okay? That means that 15% of the population, which is the individuals of the population, have this recessive disease. Okay? Now, we're going to use, of course, Hardy-Weinberg. Man, here we go. I have a pen. We're going to use Hardy-Weinberg's equilibrium to answer this. I'm going to put it right here at the top. So, it is, of course, p squared plus 2p cubed plus q squared equals 1. And if you wanted p plus q equals 1. Okay, those are the two that you need. I'm going to put a box around them. Depending on what is asked, you will use one of these two. Okay, if it asks about people, individuals, population, I'm going to use either p squared, 2pq, or q squared. If it asks about the allele frequency, specifically those terms, allele frequency, then I'm going to use p or q. Okay, so it says in this small village, again, 15% of the population is born with sickle cell anemia. That means, if you want to break this down, that means that 0.15, which is the same as 15%, 0.15 of the population equals, which one of these represents homozygous recessive? Is it, first off, we're talking about a population, so which equation is it? You should be thinking it's this one right here. Okay, because anytime we're talking about individuals within a population, we're talking about this equation here. Which one of these represents this, the homozygous recessive? That is going to be q squared. So q squared equals 0.15. Okay, I hope everybody understands. I can't ask you. I wish I could. I wish I could. I mean, I can. I know that there's Google Meet and there's Zoom, and we could try these, guys. If you want to do these, I am very much open to that. So please be aware that I'm available and very much would consider doing a Google Meet or a Zoom classroom if you guys need sort of extra assistance. If you just want to text me or email me rather, or send me a message on Google Classroom and say, hey, Mr. Eddie, I would really appreciate if me and you just had kind of a one-on-one conference so we could walk through these. I'm willing to do that, okay? So if you're looking at these and you're going, man, I'm just struggling, I don't understand. Try to, first off, when you go through these, and I hope you're going through them, I want you guys, by the way, today, I'm going to put this in as an assignment, this video. I want you guys to show me your notes on this. Okay, show me that you worked the problem. You can either take a picture of it or you can write it out on a Google Doc and upload it to that assignment. That's your assignment for tonight. I know I need to put some grades in. It's been a while. It wasn't until Friday that we decided what we were going to do for the grades. Hopefully you guys saw that. That email from Mr. Slaughter, and I was kind of waiting until then before I started putting more grades in. But I hope today, before I leave, I'm going to get some grades in for you. Okay? Maybe one of and one of those grades will be this one here soon. So, again, the first thing you need to do, you guys realize it's been like, I don't know, I've been talking about this for at least like 3 minutes, and I haven't even gotten to one of the problems yet. But I want you to understand what the question gives you first. You have to pull out of the question what is given before you can go on to the other questions. So from this, I know that 0.15 equals q squared. Now I could go on and find q, and then if I could find q, I could find p, and then I'm good. Okay, I think Mr. Bozeman said that. He said that if you can find p and q, you're golden, I think was his exact words. You can solve any problem after that. But I'm not going to do that just yet. Let's answer number one. It says, what is the frequency of the capital A allele? Notice that it used the term frequency and allele. Okay, if it says frequency and allele, which equation am I going to look at? Am I going to look at this one over here that has to do with population and individuals? Or am I going to look at this one over here that has to do with the frequency of the allele? Well, it says frequency of the allele, so I think I'm going to use this one right here. Okay, and if you're not sure, that's the one we're going to use. Okay, so it wants to know capital A. Well, which one of these represents the dominant, P or Q? Hopefully you guys are answering. You're literally talking to your screen. That would be P. Okay, so we're looking for P. This is what we don't know. That's what we want to find out. So if we know that 0.15 equals Q squared, how can I find Q? Because if I can find Q, can I find P? Absolutely. This is easy math. Okay, once you understand the variables, this is easy math. So in order to find Q, I need to get rid of this squared. So the way that you get rid of a square is you take the square root. Okay, so Q at this point, because I got rid of the square root, is going to equal whatever the square root of 0.15 is. Let me get my calculator out. So I'm going to put 0.15. I'm going to hit that square button, and I get it's an ugly number, but I get 0.3. We'll just say 9. Okay, almost 0.4. We'll say 0.39. Now, if that is Q, and I know that Q plus P equals 1, can I find P? Of course. I take 0.39. First, I'm going to put a circle around that because that's important. I'm going to take 0.39. All right. I'm going to P. We'll keep it the same. P plus 0.39 equals 1. So we're going to subtract 0.39 to get P by itself. Whatever I do to this side, I have to do to the other side. So I'm going to subtract 0.39. And if we put minus 1 there, I'm going to end up with P equals 0.6, we'll say 1. Okay? So now I have P and Q. P and Q are there. Did I answer this one? Yeah, because I was looking for P, so that one's done. Okay, if you want to, you could write it over here, P equals 0.61. There you go. Then it says, what is the allele frequency of the P allele? Well, luckily, of the lowercase p. There we go. That's not supposed to be P. I think that's supposed to be A. That's right. I forgot this one had a typo. So the lowercase a allele. There you go. If we just found that. Okay, it's real easy. By the way, use the key terms, allele frequency, so we know we're talking about that one over there, not this one right here. We haven't even used this one yet, but we just found it. Okay, if P is 0.61, then Q is 0.39. This guy right here. Okay? It's a horrible 9. All right. Now it says, what are the 3 genotype frequencies? This question is not messing around. It wants to know all 3 genotypes. Now, for those of you sitting there going, I don't understand what it's asking. It's asking for the 3 genotypes that are possible. For any Mendelian trait, if you guys recall, you can have a homozygous dominant, you can have a homozygous recessive, and you can have a heterozygous individual. It wants to know all of these. Luckily, those are represented all right here. P squared is the homozygous dominant, 2PQ is the heterozygous, and Q squared is the homozygous recessive. Now, how do I find it? Well, Q squared we already know. Okay, Q squared equals 0.15. So we're good with that one. That's your homozygous recessive. In order to find the heterozygous, we'll just start, with the homozygous dominant. So in order to find P squared, I have to take P and square it. P is right here at 0.61. So if I take the square of that, I get a P squared of whatever 0.61 squared is. So 0.61 times 0.61, you end up with 0.37. Okay, so that's my P squared. And then finally, 2PQ is 2 times P, which is 0.61, times Q, which is 0.39. Okay, so if I take that, I take 2 times 0.61 times 0.39, I get a 2PQ value of 0.4758. So you could just say 0.476. All right, so now it says what are the frequencies? So we can keep these as decimals, or you can change them to percentages. But that means that 15% of the population is going to have sickle cell anemia. 37% of the population is going to have the homozygous dominant characteristic, so capital A, and 47.6% of the population is going to have capital A, lowercase a. All right. Last but not least, it says assuming equilibrium, how many individuals out of 35,000 are going to be heterozygous? Well, how do I find that? All I do is I take the heterozygous number that I just found, which is right here, okay, 0.476, and I multiply it by 30, because remember, this is a percentage. That means that 47.6% of the people are heterozygous. So if I multiply that by the amount of people, 3,500, okay, I can figure out how many people in the population are actually heterozygous. Okay, hang on. Times 3,500. You get 1,665.3 people are capital A, lowercase a. All right, 0.15. I'm going to check something real quick. Plus 0.37 plus 0.47. Okay, so one of the ways that you can check yourself when you're doing a problem like this one with the 3 genotype frequencies is you can, once you find the values, you can add them together. So if you take 0.15, 0.37, and 0.476, it should equal 1. Because remember, this plus this plus this equals 1. So if you put those all together, by the way, you end up with I don't know if you can see that, you end up with 0.99. So you're very close to 1. That is just a rounding error. Okay, but that means, that tells you, that's kind of a way to check, that tells you that you are at least on the right track, that these should be correct because they all equal out to 1. So again, you take that value, which is normally found as a percent, that would be 47.6%. Down here, you multiply it by the number that you have, you'd end up with 1,665.3. Guys, I hope you understand, this is why this Hardy-Weinberg equilibrium problem is so important, because it enables us to look at a population and give real account to how many people have certain genotypes. And that's really important when we're talking about, like right now, if we could figure out through genetics what percentage of the population was completely immune to coronavirus, for example. Okay, if we could do that, then we would have the ability to identify those people. Perhaps maybe there's an entire town that has complete immunity because of its genetics. We could identify those people, and those people would be then beneficial to our efforts to fight against this disease because they have natural immunity, and we could harvest antibodies from them. That's just a benefit that we could use from knowing that information. So, guys, listen, I think we're just going to stop there. That's a 13-minute video. Usually I would go longer, but I think it's nice to kind of slow down and just take these one step at a time. I want you guys to do this. For homework, make sure that you understand it. If you don't, email me, text me. You don't have my phone number. Email me or get a hold of me through Google Classroom, whatever you have to do, because I am going to give a quiz over this. It's going to be open note, so that's kind of nice. But I want you guys to try and understand it. If you're sitting here and this is our second video on this and you're just like, I don't get it, I'm done, you need to contact me. Okay, I understand that you're at home. I understand that makes this more difficult, but this is hard regardless. So if you're struggling, let me know. Let's get together. Let's work on this together, okay? All right. Hey, guys, I hope everybody's doing okay. I hope you guys are staying safe and healthy. I will talk to you guys next time. Have a good one.